Hello, good morning. So today we're going to look into another process, finding the integral of functions, and that is integration by substitution. Please bear in mind that not all integrals can be solved using basic integration techniques. There are some cases wherein you are required to make use of an arbitrary variable u in order for you to solve the integral of the given function. So when we speak of integration by substitution, here we are making use of variable u to temporarily replace expressions in the integral to facilitate easier integration process. So here we will be looking into some of the expressions that can be substituted by u. So what are these expressions? So usually expressions that can be substituted by u are the expressions found in a grouping symbol. It can be the denominator of the derivative, they can be radicands, or they can be exponents. And sometimes, upon observation, you can actually identify expressions that can be substituted by u. Now, let's look into the process of substitution. Here, take, for example, this problem. We have here example number 1. So you're asked to solve the integral of the derivative dy over dx is equal to the quantity of x squared plus 2x raised to the third power times the quantity of 2x plus 2. Okay, so the first thing that we need to do here is to cross multiply to get rid of the denominator dx. So you'll be having dy is equal to the quantity of x squared plus 2x raised to the third power times, of course, the quantity of 2x plus 2. And this time around, dx is found on the right side of the equation. Then the next thing that we need to do is to identify our u. You look at the given. Here, there are two expressions enclosed inside the parentheses. So we have here the x squared plus 2x and 2x plus 2. But if you try to look at the expression, the first expression, x squared plus 2x, you take the derivative of the first expression, x squared plus 2x, the derivative is 2x plus 2, which is definitely the second expression closed inside the parentheses. So we make use of the first expression as our u. So you have here your u, therefore is equal to x squared plus 2x, and then you take the derivative of u. Okay, you take the derivative of u, so you have 2x plus 2 dx. So we are now ready to apply a substitution process. Okay, so we have your dy. This is definitely equal to u raised to the third power. How did it happen? So you replace your x squared plus 2x with the arbitrary variable u. So you'll be having u raised to the third power. And at the same time, your expression here, 2x plus 2 dx, can be replaced with du. So the whole thing, you have 2x plus 2 dx will be replaced with du. Hence, we have the equation dy is equal to u raised to the third power du. Then after that, we can now take the integral of both sides. So here we have integral of dy, and that's equal to the integral of u raised to the third power du. We can apply the basic integration technique. So the integral of dy definitely is y. The integral of u raised to the third power du is equal to u raised to the fourth power all over 4 plus the arbitrary constant c. Please take note that you need to replace u with the original expression. So your u here is x squared plus 2x. So you need to replace your u here in your final answer with x squared plus 2x. So the final answer will be y is equal to the quantity of x squared plus 2x raised to the fourth power all over 4 plus the arbitrary constant c. And that will be your final answer for this example. Now, let's proceed to example number 2. Again, you are asked here to evaluate the integral of dy over dx is equal to e raised to x raised to the third power, e raised to x over 3 rather. So Here, the first thing that you need to do again is to cross multiply to get rid of your dx in the denominator. So your new equation will then be dy is equal to e raised to x over 3 dx. You identify your u. So definitely here our u is the exponent x all over 3. So your du, you take the derivative of both sides of the equation. So your du here is equal to dx all over 3. Your du all over dx is 1/3, or your du is equal to dx all over 3. But in the given, we will only be needing dx. So in our equation here, du is equal to dx all over 3. We get rid of your 3 in the denominator found on the right side of the equation by simply multiplying both sides of the equation by 3. So we'll be having the equation 3 du is equal to dx. So in our substitution process later on, we can actually substitute your dx with 3 du. Okay, so here our new equation will now then be equal to dy is equal to e raised to u. We substituted your exponent x over 3 with u. Okay, so e raised to u times your dx can be replaced with 3 du. So we have the quantity of 3 du here. And please bear in mind the constants should be written before the expression. So we have our new equation dy is equal to 3 e raised to u du. And if you can still recall in our lesson in derivatives, the derivative of e raised to u is equal to e raised to u. And if you take the integral of e raised to u, definitely the answer is e raised to u plus the arbitrary constant c. So here, if you take the integral of both sides, your integral of dy is equal to, of course, there's a constant here. You must factor out the constant 3, and then you take the integral of e raised to u du. And I said a while ago that the integral of e raised to u is e raised to u plus c. Therefore, your answer will then be y is equal to 3 e raised to u plus the arbitrary constant c. Then again, you need to replace your u with the original expression. So your final answer will then be y is equal to 3 e raised to x over 3, which is the original expression, plus the arbitrary constancy. Okay, so that's how you're going to apply integration by substitution. Now we have here example number 3. Okay, let's try to look at example number 3. So we'll be getting the integral of trigonometric functions here. Okay, anyway, you're aware of the derivative of basic trigonometric functions, so it's easy for us to get the integral of basic trigonometric functions. So for our example number 3 here, you're asked to solve the integral of the derivative dy over dx is equal to sine x raised to the 6th power times cosine x raised to the 3rd power. Okay, again, we need to cross multiply. So your dy will then be equal to sine x raised to the 6th power times cosine x raised to the 3rd power. Then your dx will be written here on the other side of the equation. Okay, now we identify our u. Take note that if you take the derivative of that trigonometric expression, it should be found also in the remaining expressions in the derivative. So here we decide that your u is equal to sine x. Okay, and then you take the derivative of u. You're aware that the derivative of sine x is cosine x dx. Okay, so there's a thing that we need to do in the original equation. So we are going to factor out your cosine x here in your cosine x raised to the 3rd power to apply one of the trigonometric identities, the Pythagorean identities, for us to be able to get the integral easily. So we will be having the equation dy is equal to sine x raised to the 6th power. This time, we need to factor out cosine x raised to the 2nd power. Then the remaining expression is cosine x dx. This is the same with cosine x raised to the 3rd power. Okay, so we did not change the equation. But here, uh, we need to substitute your cosine x raised to the second power with the Pythagorean identity. Okay, so you're aware that your cosine x squared is equal to the quantity of 1 minus sine x squared. Okay, so we discussed that when you were still in the grade 9. So our new equation will now then be equal to dy is equal to sine x raised to 6 power times the identity, which is used to replace your cosine x raised to the second power, and that's 1 minus sine x raised to the second power times, of course, the remaining expression here, which is cosine x dx. Then after that, since we made use of u as a substitute for your sine x, we can now replace your sine x raised to the 6th power by u raised to the 6th power. And again, we are going to do that also in the terms inside the parentheses. So you have the quantity of 1 minus, you replace your sine x with u, so you'll be having 1 minus u raised to the second power, times, of course, the derivative of your u, okay, which is du, and that's cosine x dx. We can therefore replace your cosine x dx here with your du. Then after that, there's a need for you to multiply your u raised to the 6th power to the terms inside the parentheses. So you'll be having u raised to the 6th power times 1, you have u raised to the 6th power, and then u raised to the 6th power times negative u raised to the second power, that will give you u raised to the 8th power. Well, of course, you have here your du. Okay, then after that, anyway, your du here is distributive by nature, so you'll be having dy is equal to u raised to the 6th power du minus u raised to 8th power du. And of course, here you can now take the integral, and then you apply basic integration techniques. So you have here integral of dy is equal to the integral of u raised to the 6th power du minus the integral of u raised to the 8th power du. Okay, so applying basic integration technique, you have your integral of dy as y, and then your integral of u raised to the 6th power du as u raised to 7 over 7. You're aware, anyway, you're aware of the basic integration techniques. Okay, so minus u, the integral of u raised to the 8th power is u raised to the 9 power all over 9 plus the arbitrary constancy. Then you replace your u with the original expression. Please bear in mind that we substituted your u here in this example with sine x. So therefore, your final answer will then be y is equal to sine x raised to the 7th power all over 7 minus sine x raised to the 9th power over 9 plus the arbitrary constancy. So that will be your final answer. Please bear in mind that your sine x raised to the 7th power can be written also as sine, then you have the exponent 7, and then followed by x. Okay, they mean the same thing. Okay, I can accept that as your answer also. Okay, so that's your final answer for this example. Now, we look at example number 4. So here, again, we will be applying integration by substitution, but you're asked to solve the integral of dy over dx is equal to ln of x over x. Okay, again, we get rid of your dx in the denominator first. We do cross multiplication, so your dy, your new equation, will then be equal to dy is equal to ln of x all over x dx. So we identify again your u. Here our u is ln of x, and you're aware, okay, that the derivative of ln of x is 1 over x. So du therefore is 1 over x dx, or dx all over x. Then substituting u and du in the original expression, or in the original equation, will be having dy is equal to your ln of x here. Your ln of x will be substituted with u. So you have your u here, and then your dx all over x will be substituted by du. So your new equation will now then be equal to dy is equal to u du. Again, applying basic integration techniques, you'll be having integral of dy is equal to the integral of u du, and that will give you y is equal to u squared all over 2 plus the arbitrary constancy. You replace your u with the original expression, that is ln of x. So therefore, your final answer will then be equal to the quantity of ln of x raised to the second power all over 2 plus the arbitrary constancy. So that's how you're going to use integration by substitution.